Okay, good morning. Welcome back to the hottest the Homotopy Type Theory electronic seminar talks. Today, we're very happy to welcome Loïc Pujet, who's going to tell us about observational type theory meets the calculus of inductive constructions.
Yeah, thank you. Thank you very much. So, well, first, I would like to thank the organizers of the hottest seminar for inviting me. And today, I'm going to present joint work with Nicolas Tabarot regarding, as Emily said, the marriage of observational type theory and the calculus of inductive constructions, hence the title of the talk. So, well, first, let me give a brief description of the objects, well, actually the type theories that I will be talking about. So first, observational type theory. It was developed in the early 2000s with notably the seminal paper of Altenkirch, McBride, and Swiestra. And basically, the whole point of observational type theory is to extend intentional type theory with extensional reasoning principles, such as the extensionality of functions or the extensionality of propositions, and to do this without sacrificing computational properties. Well, because as I'm sure most of you will already know, the inductive equality of intentional type theory is very underspecified in the absence of the univalence axiom. So the idea behind observational type theory is to swap this underdefined intentional equality with the so-called observational equality, which is a propositional relation that is defined on a type-by-type basis. And because of its definition, the observational equality will happily support the principle of function extensionality and can straightforwardly be extended to support more principles such as the extensionality of propositions or bisimilarity of co-inductive types and whatnot. So far it sounds very similar with the features of a univalent equality, but there is a central difference, which is that in observational type theory, the equality is always propositions in the sense that it is, well, let's say -1 truncated. So since the equality is always a proposition, it means that every type is always a set. Thus, if homotopy type theory is the language of higher groupoids, then observational type theory would be the language of sets and propositions. And on the other hand, we have the calculus of inductive constructions, which is the type theory that underlies both the Coq proof assistant and the Lane proof assistant with minor tweaks on both sides, but this is not very important. And the calculus of inductive constructions is a very powerful type theory comparable to classical set theory in terms of logical power. And its strength comes from two features that it adds on top of intentional type theory. The first of these features is a comprehensive class of inductive types, which encompasses the usual W types, but also indexed types, such as the inductive equality or vectors, which are lists indexed by size. And the second major feature of the calculus of inductive constructions is a bit more discrete at first sight, in that a new user of type theory will tend not to think about it too much, but it hides a tremendous amount of expressive power. I am, of course, talking about the impredicative universe of propositions. Impredicative means that this universe is closed under arbitrary quantification. So if we have a proposition B that depends on a type A, then the dependent product by AB will live in the same universe of propositions as B, even if the type of A happens to be, well, much larger. And in the variant implemented by the Coq proof assistant, there are two such sorts called respectively prop for the sort of proof-relevant propositions, and S prop for proof-irrelevant propositions. We will come back to this distinction a bit later. And so you can compare this behavior with the universe type, which is not impredicative, because it's actually not a single universe, but it's really a hierarchy. The universe type 0 is smaller than the universe type 1, which is smaller than the universe type 2, and so on. And then when we form a dependent product whose codomain is a type and not a proposition, then the sort of the dependent product has to be larger than both the sort of the domain and the sort of the codomain. Okay, so now for a bit of motivation. So why do we want to merge observational type theory and the calculus of inductive construction? Well, the main reason is that we would like to have access to the features of observational type theory inside the Coq proof assistant. This would be very useful in practice, since most of mathematics, including the mathematics that is used in computer science, rely on extensionality principles and, even more importantly, quotients. And there are several ways to encode both of these in the Coq proof assistant, including just postulating them as axioms. But no matter what, you will not get a proper computational content. And this makes quotients very inconvenient to use in practice. And users who care about computation often will have to resort to giving effective presentations of their quotients with canonical representatives of every equivalence class, or the other alternative is to use setoids, which is a whole mess. And so far, the only kind of non-observational proof assistants that really handle quotients are the cubical proof assistants, which do work fine, but they are quite complicated to understand in that you don't want to tell a compiler engineer that they have to learn the basics of count-filling operations to prove their soundness theorem. And even for a seasoned type theorist, actually, doing set truncated mathematics in cubical AGDA is hardly a pleasant task. We do not want to have to prove that everything is a H set by hand, and carrying around all these burdensome proofs is not very convenient. This is basically the setoid hell all over again. So we want something more convenient than that. And finally, an argument that might interest the categorically minded people is that an extensional type theory with impredicative propositions is very much reminiscent of what is available in toposes. Thus, a mixture of the calculus of inductive constructions and observational type theory could be a good candidate for an internal language for toposes, which would come in very handy when one wants to formally prove a result that takes place in toposes. Thus, we need to make sure that observational type theory plays nicely with the features of the Coq proof assistant. So this has been going on for a while, and with my co-author, we have developed several formal systems that get every time a bit closer to an actual observational Coq proof assistant. And the last iteration that incorporates pretty much all of the ingredients is what I'm going to talk about today. Okay, so this was for the bird's eye view. Now, let us see how observational type theory works in practice and how it can provide extensionality principles while preserving computation. So the first brick of observational type theory is, of course, the observational equality. to implement it into the calculus of constructions, we equip any inhabitant of the type sort with a relation that is valued in S-prop. And we write this relation with a tilde, and we call it the observational equality. S-prop here means that this is a strict proposition, or in other words, that any two witnesses of observational equality are not only equal, as they would be if it was only a H proposition, but they are even convertible, so definitionally equal. This entails that proofs of observational equality cannot contain any computationally meaningful information. And this is both a curse and a blessing, because it means that we can basically postulate any theorem that we would like as an axiom, and it will not block computation, since it will never even be considered by computation. Thus, we postulate our desired extensionality principles, which include function extensionality, the extensionality of propositions too, and also a transport operator for propositional predicates. Remark that we can only postulate it for propositional predicates and not type-valued predicates, because in the case of a propositional predicate, well, the whole type is a strict proposition, so we can postulate it as an axiom and it will not interfere with computation. But in the case of type-valued predicates, we will have to work a bit more, because if we just postulated it, then it would block computation very fast, since it is not in the propositional layer of the theory. Note that in most formulation of observational type theory, including the original one by Altenkirch et al., these principles are usually not taken as mere implications, but as definitions. The observational equality between two functions would be definitionally equal to the statement of function extensionality. However, in our framework, we found that requiring only implications is more elegant and generalizes more readily to the inductive types. And really, it's a bit of a trade-off. Like, on the one hand, it's usually nice to have more computation rules, so more definitional equalities, but it can also be a bit surprising for a user of a proof assistant when the equality type magically turns into a very complicated proposition that unfolds a lot of stuff. So, well, in this case, we have chosen to not take the extensionality principles as definitional equality, but as implications. All right, so the principles of extensionality and transport are enough to fully specify the observational equality in the case of dependent products, and inductive types too, because we can combine transport with the induction principles of inductive types to get a concrete formulation of equality, which can be expressed usually as an inductive proposition. So just this handful of axioms is enough to fully characterize the observational equality on the basic types. But it remains completely unspecified on the universe so far. And when you think about it, it's really the most important case. Well, not necessarily the most important, but the most interesting. Because contrary to all the types so far, the lowest universe of type theory naturally has the structure of a groupoid and not of a set. Well, at least that's what we would get from the univalence axiom. But of course, in observational type theory, all types should be sets. Thus, in first approximation, we will ask for the injectivity of type constructors, which means that a function can only be equal to another function type, the equality between a function type and, say, an inductive type will always automatically reduce to, well, imply a contradiction. But not only that, but also we ask for injectivity of the dependent products. So if two function types are equal, then their codomains and their domains will be respectively equal. This is maybe surprising even for someone who is used to set theory, because, well, in set theory, this is completely not true. For instance, the functions from the empty set to the empty sets, this set is the same as the set of functions from the empty set to, say, the Booleans. So it seems to contradict the standard formulations of set theory, and not only univalent mathematics, but also set truncated mathematics. But as we will see, this is not really a problem. All right. So this is just for the definition of the observational equality. But we still need a way to eliminate it. And since it does not contain any computational information whatsoever, we will need to find another way to have the eliminator compute. And the eliminator that we will use is called the cast operator. And basically, it takes two types, A and B, with a proof that A and B are observationally equal, as well as an inhabitant T of A. And with all of that, it will provide an inhabitant T of B. Since it cannot compute on the witness of equality, since this is a strict proposition that does not contain any information, it will instead compute by inspection on the types A and B, more specifically according to their head constructors. For instance, if you form a typecast operator between two functions, then it will reduce to a kind of back and forth function that will take its argument, cast it to the other domain, then apply the function that I forgot to write in my formula, and cast the result back to the desired codomain. Sorry, I just have to plug my computer or else it will turn off. Give me 1 second. Is everything fine? I can go on.
Please continue.
Okay, good. Yes, I was saying that the cast operator will compute according to the head constructors of the two types A and B. And in the case of matching head constructors, it will reduce, well, on a type-by-type basis. And in the case of non-matching head constructors, then it will use the fact that the equality between non-matching head constructors implies a contradiction to simply produce a dummy element of the second type. And at first glance, this cast operator seems a bit less general than the usual J eliminator of the inductive equality. But in fact, because of proof irrelevance, we can derive the J eliminator for type-valued predicates. So if we take a type A with an inhabitant and a predicate that is valued in types, we can use the cast operator to realize the J eliminator. So we have the full generality of Martinov type theory. Now, let us think about the indexed inductive types. So the first observation is that it's not so easy as the dependent products, because we will, in a full generality, we will need to add some new normal forms. For instance, we can use the scheme of indexed inductive types to define the inductive equality, which is just the usual definition. And using the induction principle for this inductive equality, we can actually show that it is equivalent to the observational equality. It's usually what happens when you have two different notions of equality in the same theory. So this entails that function extensionality becomes provable for the inductive equality, which is very different from what we have in bare Martinov type theory. And this implies that not every closed proof of equality will reduce to a proof by reflexivity, since using function extensionality, we can produce some complicated proofs of equality between two integer functions, and we have no hope to reduce all of these to reflexivity, since this would be non-decidable. As a consequence, we first apply a transformation to all of our inductives, which is standard, the standard way to convert an index into a non-uniform parameter. So compare the definition of the inductive. It uses, well, the standard definition of the inductive uses two parameters, A and A, large A and small a, and an index of type A. If we convert the index in a non-uniform parameter, we get a new parameter B, and the constructor reflexivity will take a new argument, which is an equality between A and B. And this can be done in a very systematic manner. And if we add this, then we recover the canonicity theorem, in that every closed proof of equality in our new type theory will actually reduce to a proof by reflexivity, well, at least this extended reflexivity. So it will pack the proof of observational equality, basically. A second observation that shows that it is not so easy to support the general indexed inductive types is that, well, we have to think a bit when we define what it means for two inductive types to be equal. If we decide to take inspiration from the injectivity of type constructors that we used for the equality of the universe, we would get problems, because using the typing rules of the Coq-proof assistant, if we define an inductive types that contains no constructors, then it will land in the smallest universe, even if it has a parameter that lives in a large type, in this case, the universe of types. If we decided to say that equality between empty A and empty B implies the equality between A and B, which would correspond to injectivity of the type constructor, then we would get basically a retract of the universe of type inside the universe of type, which is inconsistent in an impredicative type theory. So instead, we will use a different strategy, which is that the equality between two matching inductive types will imply the equality of all the arguments of the constructors. So in the case of the empty inductive type, well, it will be vacuously true. Let's say how it works on a slightly more complicated indexed inductive type, which is here the type of vectors or lists indexed by a size. So the traditional definition of the type of vector will have one parameter that is the type of the elements of the vector, and one index that is an integer and has two constructors. If we do our little transformation to convert indices to non-uniform parameters, we will get something that looks like this. We get a new parameter of type integer, or natural number, and we will have two new arguments in the constructors that are basically observational equalities. And so what does it mean for two types of vectors to be equal? Well, we decide that if the type vect a n is observationally equal to vect a prime n prime, we will obtain in proof of observation, a proof of observational equality between all the types of that intervene in the constructors. So here you can see that in particular it entails that A is observationally equal to A prime, and also that n is observationally equal to n prime, even though this is not immediate and we have to do a proof by induction from V nil epsilon 1 and V cons epsilon 3. And with all of this, we have a definition that handles all inductive types properly. Now, let us think a little bit about impredicativity, because when we think about it, we have an impredicative sort of strict propositions that contains the observational equality, but it supports with the cast operator large elimination for this observational equality. And this setting is very similar to what we have in Lean, because in Lean we have an inductive equality that lives in a universe of proof-irrelevant propositions. And this is a bit worrying because Abel and Coquant proved that the algorithm that is used by Lean to decide type checking is actually non-terminating because of the interference between impredicativity and proof irrelevance. So Abel and Coquant constructed this example, which is, well, in that case, it's translated to the language of observational type theory. And so we see that the bad term that was designed by Abel and Coquant in the case of the type theory in Lean can be replicated inside our observational version of the calculus of inductive constructions. So should we be worried? Well, actually we should not, because when we think about it, this bad term is a proof of a strict proposition. So it is not computationally relevant. And thus we have no reason to actually try to normalize this term. We should really just keep it as a proof, and simply by the properties of strict propositions, we will never need a normal form to decide convertibility. So really, this is not an issue. And now let's look at the semantics a little bit. So first, the models in Grothendieck toposes. So as proved by Daniel Gratzer, this kind of observational type theory can be modeled in any Grothendieck topos, where the interpretation of the universe hierarchy will be inductively built to contain codes for every object of the topos. So let's just look at the definition of what will be the interpretation of the universe in a topos. So first, we assume that we have a hierarchy of strict universes for the topos, which always exists in Grothendieck toposes, as proved by Sterling et al. And from this, we can use a small induction to build a new hierarchy of universes, which will basically equip the elements of the universe hierarchy with a label that indicates how this type has been built. For instance, a type can be labeled as a dependent product, which indicates that it has been built using an introduction rule for a dependent product. But the same type can also be labeled as an arbitrary type, in which case we get absolutely no information on how it has been built. And this is sufficient to define all the primitives of observational type theory on this new universe hierarchy, just by ignoring the fact that some types will be encoded with different codes in the universe that we are building. For instance, the type of functions from the empty type to the empty type will have two different representations. One as a type labeled by the fact that it is a bitype, and one that is unlabeled.
Loïc, could I interrupt you with a question or a remark?
Yes, please.
Just the slide
sorry,
has disappeared.
I should not. Yeah.
I just wanted to remark that the people might be confused. The strict in given a hierarchy of strict universes has got nothing to do with the strict in S prop, right? So it's right. It's to do with this realignment property, which probably isn't very well known to most people.
Exactly. This is basically a technical detail, and I should not have written that word as it is.
Okay. Well, it's a very interesting thing.
And thus, with this interpretation of the universe of observational type theory, we get that any theorem that we proved in our observational type theory that quantifies on the universe will actually be interpreted by a function in the topos, in the grothendieck topos, that can apply to any type inside the grothendieck topos. So this universe, even if it is a bit redundant, contains codes for every type of the grothendieck topos. And as a simple corollary to this model, we get that our observational type theory is consistent, since, well, we can build a non-trivial topos as soon as we assume the axiom of set theory. And now the question is this type theory a reasonable language for one-toposes? Well, it's a bit of a mixed bag. First, remark that it is much more powerful than the theory of elementary toposes, because we get not only a natural number object from the fact that we have inductive types, but also some limited amount of replacement enough to define the sum of natural numbers, the parts of the natural numbers, the parts of the parts of natural numbers, and so on, which is normally impossible to define in the theory of elementary toposes. But on the other hand, we are missing some principles from the theory of elementary toposes, this principle is the principle of unique choice, also called the principle of function comprehension, which says that if you have a relation between two types A and B, such that it is a functional relation, then you can extract a function from A to B that realizes this relation. And this is a basic building block of the theory of toposes, but it is not available in our observational type theory. As a substitute, we could have a propositional version of it, which replace the sigma type in the conclusion with an existential type. Since this is a straight proposition, we can just freely postulate it, and as long as it is consistent, it will not cause any kind of trouble. Yeah, but however, if we postulate the version with the sigma type, then we will not get proper computation principles. So yeah, it's a bit of an in-between the theory of elementary toposes and say a full language for grothendieck toposes. Okay, so this is the part of the semantics in toposes. Now let's look a bit at normalization models, which we use to prove computational properties of our theory, in particular that every well-typed term is normalizing, and as a consequence that the typing relation is decidable. To prove this theorem, basically we built a normalization model inside Martinov type theory that we fully formalized in the Agda proof assistant using the framework of Andreas Abel et al. And we have to be a bit careful when we do this, because we cannot really use the standard way to interpret the universes, since the cast operator is fundamentally non-parametric. And that's the only way we found to deal with such a non-parametric operator in our theory is to use a proof-irrelevant reducibility predicate instead of the maybe simpler proof-relevant reducibility predicates that have been championed by several influential members of the community in recent years. And unsurprisingly, this prevents us from supporting the universe of proof-relevant propositions in our model. Because, well, if we were to add proof-relevant propositions, then we would be forced to compute with them. And thus, the counter-example of Abel and Coquant that we talked about a little bit earlier would apply and break the type-checking algorithm. But with a simple trick, we can actually have an impredicative universe of strict proposition simply by, well, being very lax in their interpretation, basically having a minimalistic reducibility predicate for strict propositions. And with this, we can actually get a full normalization model. And the funny part is that we can build this normalization model inside of Martinov type theory, which is a very weak type theory. It's not even impredicative. So it might come as a surprise that we are able to prove normalization for an impredicative type theory in a predicative one. And really, this is connected to the lack of unique choice. Because in our type theory, we have a difference between the functions that we can define as terms of type nat, arrow, nat, and the functions that we can define using impredicativity as functional relations. So even though we can use the impredicativity to define some super complicated functional relations that entail, let's say, that Martinov type theory is consistent, we will not be able to extract them to actual terms of type nat, arrow, nat without the principle of unique choice. And thus, this has the interesting corollary that every integer function that we can define as a closed term of type nat, arrow, nat in our observational calculus of construction can also be defined in the much weaker Martinov type theory. So we do not really get the full computational power of impredicativity. We only get the logical power of impredicativity. We can prove that, say, system F normalizes, but we cannot extract a function that computes a normalization for system F. And I will conclude on an interesting corollary, which is that the same property applies to the univalence axiom. Every integer function that we can define as a closed term of type nat, arrow, nat in Martinov type theory augmented with the univalence axiom can also be defined in bare Martinov type theory. And in order to prove this, we can use the cubical model of Coquant, Cohen, Huber, and Nordberg to embed Martinov type theory with the univalence axiom into our type theory observational calculus of constructions. This proof has been mostly formalized in the Coq proof assistant, but not completed yet. Especially, it is lacking the case of the universe, which is the most difficult one. And this basically reaches the end of what I had to say. So thank you for your attention. And if you have questions, I will be happy to answer them.
Great. Thank you so much. Let's have our round of visual applause. All right, who would like to ask the first question?
I'll ask a question, Loïc. So this is sort of the evolution of a series of things that you guys have been doing, Nicolas and you and so on. Is this the end, or is there something more that you want to have?
I guess the end goal is to have it inside of the Coq proof assistant. And if we really want to support all of the small extensions of the Coq proof assistant, I guess we would have to pay a bit of attention to, say, the co-inductive types, or to say cumulativity, universe polymorphism and whatnot. But I guess realistically, this is the most complete type theory that we are willing to actually prove stuff about, and especially prove formal stuff about, because the proofs are becoming very complex and we are reaching the limits of the Agda proof assistant. We get developments that take something like 1 hour to type check. So yeah, I guess we will not go much further than that.
I'll ask a question. This is also about going further. So what about the higher observational type theory that Mike Schulman has proposed? Is there any ideas about how this could be adapted to include higher structure?
Right. This is a very good question, and I'm following with attention what is going on with Mike Schulman and his co-authors. But so far, I don't know much about higher observational type theory. And in particular, I don't really know if we have reasonable models. I don't really know if it is terminating. It is a whole uncharted territory. So I don't really know is the best answer that I can provide, I guess. And the same goes for adding this into the Coq proof assistant. So far, there is, I mean, it is on, it is too much of an uncharted territory to envision integration into a very cautious proof assistant such as the Coq proof assistant.
Thank you.
May I ask another question?
Yes.
So I use Agda a lot in the sort of, postulate a few useful things and continue without caring about whether you've destroyed the power to compute canonical forms, which don't matter to me so much. And doing that, one thing I find incredibly useful is rigorous and extensive use of heterogeneous equality. What Conor McBride called John Major equality. Would there be a version of what you're doing where you have a heterogeneous version of observational equality? Would that make it any different, or would it be better or worse, or not really an issue?
So actually, the original formulation of observational type theory of McBride et al. Uses a heterogeneous equality. And we really had some back and forth hesitation between a heterogeneous version and the homogeneous version. But really, in terms of properties, this is the same theory. This is only a matter of convenience for the user. And on the one hand, the homogeneous version asks for more transport to state say what is the equality between dependent products, because like in my presentation, I have only shown what it would be for non-dependent product, which is simpler. So yeah, the homogeneous version is a bit more technical, but it is perhaps less surprising for someone who comes from mathematics than the heterogeneous version, which has some very surprising properties, such as being non-transitive, unless you do an equality which is a path over an equality between types. The heterogeneous equality would be non-transitive, which is, say, a bit surprising for most people, I would guess. And also, really, one thing that helped us decide on a homogeneous version is that the fundamental brick of this type theory is really the typecasting operator, which is intrinsically homogeneous. You do not do heterogeneous typecasting. It's only between equal types, and both types will be in the same type, which is the universe. So really, I feel like observational type theory is more intrinsically homogeneous. But yeah, to answer your question, heterogeneous version would work fine too. And it would be basically the same theory.
Thanks very much. Thank you.
So my question is essentially just for you to repeat yourself. You made an interesting point earlier in the talk about how it was more advantageous to postulate something like function extensionality as a implication rather than anything stronger. Could you just remind us?
Right. Where did I write that? Yeah, here. So it could be a definitional equality instead of an implication. And actually, we even proved all the meta-theoretical properties, including normalization and decidability of conversion for a version with definitional equality. But in the end, we went for the implication version just because it generalizes better to the case of inductives, which get much more tricky to handle with, well, maybe not more tricky, but less elegant to handle with definitional version. So really, it's a matter of taste, I guess. There's nothing really deep behind that. I think it's a bit less restrictive if you use an implication, since probably like it gives a little bit more leeway in the models, I guess, where strict stuff does not have to be strict anymore. But yeah, it's a technical detail.
Great, thank you. Any final questions?
Do you think that this theory is in some sense a truncation of homotopy type theory?
This is a good question. I assume that to say that such a theory is a truncation of homotopy type theory, you would need some kind of conservativity result, which says that if some result that can be phrased in some restricted language can be proved in homotopy type theory, then it can be proved in, well, its truncation can be proved in our theory. I'm not really sure. One thing that is for sure is that impredicativity in homotopy type theory is not included, at least in the most standard version of it. So in that way, our theory goes a bit further in that direction. But I would assume that yes, a statement that can be proved in homotopy type theory, well, it is conservative over some fragments. I don't really know which fragment.
I'm sorry, what I meant by truncation, I meant in the sense of set truncation, because the cast rules seem kind of like a restricted univalence in that it seems to equate different types in a surprising way.
Yes. So you have for the observational equality, you have some equalities that are not derivable with the univalent equality. In particular, these injectivity properties that say that when two function types are equal, then you get that both their domains and codomains are equal. So in that sense, you could not hope to prove that in homotopy type theory and truncate it and get the same result. Yes, I guess, does this answer your question?
Yes, thanks.
Can I ask a question?
Yes.
Actually, it's not a question, it's a remark. So I think for the previous question, the fact is that in homotopy type theory, unique choice is just true, right? It just holds. So it wouldn't be able to prove everything that you prove in homotopy type theory. And unique choice is used implicitly very often in homotopy type theory. So I don't think that it will be conservative. Well, it would prove. I don't think it would answer positively the question of the previous question.
Right. Although I would say that without resizing rules, homotopy type theory is predicative, and in that case, you can prove the predicative unique choice principle in our theory too, I assume, if you just define the type of H propositions, not in the universe of strict propositions, but in the universe of type. I don't think you need univalence to show the principle of unique choice.
No, univalence is not needed. Yeah.
So you could prove it too, but
then it means you need to work with a different type of propositions.
Yes.
Yeah.
But for the conservativity result,
yeah,
it might be sufficient.
Thank you.
All right, if there are no further questions, let's thank the speaker again. No.